A block of mass m1 rests on a horizontal surface and is connected by a light string that passes over an ideal frictionless pulley to a hanging block of mass m2. The coefficient of kinetic friction between the horizontal surface and the block is μk. The system is released from rest, causing the hanging block to descend a distance d. Assuming the string remains taut, the pulley is massless and frictionless, and the acceleration due to gravity is g. Derive an expression for the speed of the blocks after the hanging block has descended the distance d. And we're told to express our answer in terms of the variables described earlier and given to us. So this is a picture of what the problem is basically describing. So you have one block m1 that's sitting on the surface and another block m2 that's hanging off and being pulled by gravity. And we're told to find the speed after it has descended at distance d. So perhaps let's start with drawing all of the forces on these two blocks in free body diagrams. So if we draw the free body diagram for block 1, say that this is the center of block 1, then block 1 has the forces. Here we have the normal force that points up. So this is for block 1. And the normal force is from its contact with the surface. And then pointing downwards, we have the block's weight, which is given by m1 times g. To the right, we have the tension force from the taut string. And to the left, we have the force of kinetic friction that slows it down. Because we're assuming that the block is descending, so m2 is going down, and the pulley pulls m1 towards the right. So this is for block 1. And then now let's draw it for block 2 as well. So for block 2, instead we have the tension force going up this time, if we look at it here. And downwards we have the weight of block 2, which is this m2 times g. And that accounts for all of the forces acting on them in this system here. So now we can write down our force equations. So we can use Newton's second law, which says that the net force acting on an object is equal to the mass times the acceleration. And in this case, we can break it down into all of the y forces, the forces acting in the vertical direction, and all of the forces acting in the horizontal direction. So for block 1, let's choose, and for each of these free body diagrams, we can choose the axes in any way we want. So for block 2, I'm going to choose this direction to be the positive y direction. And this is just for convenience because the block is moving downwards. And for block 1, I'm going to choose the axes so that the positive x direction is towards the right and the positive y direction is upwards. So for block 2, I can also draw an x direction. So now that we have this set up, we can go ahead and apply Newton's second law to each of these blocks. So let's start with block 1. I'm just going to write the number here. So this is for block 1. So let's start with the x direction. In the x direction, we have the tension and the force of kinetic friction. So from this, we get that the tension points in the positive x direction as defined here, and the force of kinetic friction points in the negative x direction. And that's all the forces in the x direction. So we set that equal to the mass of block 1, which is m1, times its acceleration, a. And also, let's do it for the y direction. This time, we have the normal force pointing in the positive y direction, and the weight points in the negative y direction. And that's equal to the mass times the acceleration in the y direction, which is 0. So this term cancels out and becomes 0. So if we are here. And now let's do the same thing for block 2. For block 2, since we picked the positive y direction to be downwards, and you don't have to do this, you could also pick it pointing upwards. You'll just have different signs for your acceleration. We can write that the summation of the vertical forces for block 2 is just m2g, which points in the positive y direction defined here, minus the tension force, which points in the negative y direction here. And that's equal to the mass of block 2 times the acceleration of block 2. And since these two blocks are connected by a taut string, A1 equals A2. So the blocks both accelerate at the same rate. So I'm just going to replace both A1 and A2 by just the letter A for simplicity. So this becomes M1A and this becomes M2A. And now, if we can somehow solve for A, then we can actually perhaps use kinematics to figure out what the velocity will be after it falls a distance d. So let's start by figuring out how we can get to A. So first notice that we have this force of kinetic friction here that is currently unknown. But we have a formula that says that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And we also right now don't know what the normal force is yet, but if we notice, this equation can be solved to give us the normal force. So if we arrange this by adding m1g to both sides, we get that the normal force is equal to m1g, or the weight of block 1. So with that, we can write the force of kinetic friction as the coefficient of kinetic friction times m1 times g. And so now we've used this equation and now we have eliminated the force of kinetic friction and written it in terms of the known constants that we were told to. So now we still need to figure out what the tension is. And now this is just a system of two equations and we can solve for t. So if we rearrange the second equation so that t equals m2g minus m2a, and then we can plug this value of t into the first equation. So we have that m2g minus m2a, that's from here, plug it into the first equation, and minus Fk, which is the force of kinetic friction, which we also have an expression for here. We can plug that in too. And we can set that equal to m1a. And so now we just have a in this equation. We have it here, and we just need to solve for a. So I can move all of the a's to one side, so we can have m1a. If we add m2a to both sides here, so we could have m2a here, but I'm just rearranging it so that the a's are on the left side instead of the right. And that's equal to whatever's left on this side. Okay, I'm gonna clean this up a little bit so that we have more room. And then we can factor out the a's from the left side. And factor out the g's from the right side. And you don't have to factor out the g's, but it does make it slightly more compact. And then we can just divide by m1 plus m2 on both sides to get that a equals g times m2 minus mu k m1 divided by m1 plus m2. So now we have an expression for the acceleration, and it turns out that it is expressed in terms of a bunch of constants. So we actually have constant acceleration. So because we have constant acceleration, we can actually use the big four kinematic equations. So let me just get rid of all this to make more room. So we have one kinematic equation that says that the final velocity is equal to the initial velocity squared, or final velocity squared is equal to initial velocity squared, plus 2 times the acceleration times the displacement, or distance d. So we can use this to figure out what our final velocity will be after going a distance d. And we have the acceleration a that we can just plug into this. And furthermore, we know that v0 equals 0 because the system is released from rest. So now if we plug all of this in, first let's drop this v0 term. And I'm going to drop the subscripts for this one too, but this represents the final velocity. So the final speed squared is equal to 2 times a times the distance d. So v is equal to the square root of 2ad. And now I can just plug in a into that expression. So v equals the square root of 2. We can plug in a, so that's g times m2 minus mu k m1, and we still have this d at the end, and this is going to be all over m1 plus m2, and this is the final speed, so this would be our final answer. And so there are like multiple ways to do this problem. So for instance, you could use energy principles where you figure out what the work it being done by friction is, and you set it equal to the change in the energy of the system of this pulley and the earth. But it turns out that if you use energy, it's about the same. Like the derivation length is about the same. So, and in this case, we chose to use forces, but you could use energy as well. And that is how you would solve this problem here.